Welcome back. In the last class, we discussed about scalar interaction and we worked out the energy level diagram for two coupled spin systems, weakly coupled spin systems A and X. We identified the four energies and total magnetic quantum number of each energy states and found out the transition probabilities, allowed transitions for each of these spins. We found out there are two transitions for A and two transitions for X. And we are, of course, from the energy level diagram, I explained to you alpha alpha and beta beta are unpaired states and they get destabilized and have higher energy and moves up by J by 4, whereas alpha beta and beta alpha are paired states, they are stabilized. So they have lower energy and push us down by the same amount by J by 4. So when we worked out, we found out for two couple spin system, we get 4 peaks, 2 for A and 2 for X. Find the center of the chemical sheet of A. There are 2 peaks, which are 1 peak to the right of J by J by 2, 1 peak to the left by J by 2. Same for X. Now we went to 3 spin system, and I showed there are 8 possible energy states, and worked out what is the magnetic quantum number of each energy state, and I explained to you there are 12 possible transitions here. 4 for A, 4 for M, and 4 for X. Okay. I explained to you in this diagram. I showed you this is the energy state with the total magnetic quantum number for this minus 3 by 2, and each of this energy state has total magnetic quantum number of half, and this one has magnetic quantum number of each energy state is minus half. For this it is 3 by 2 pertaining to the orientation of different spins, different magnetic moments, whether it's up or down. We can work out all the energy states. What are the possible energy states? And we found out also what are the allowed transitions for all the 3 spins, A, M, and X. I don't want to go into the details because we discussed this in the last class. Just to see only A transitions also we will see, or X transitions. See, in this case, beta of X is changing to alpha of X with a change in the magnetic quantum number from between these two energy states is 1. From 3 by 2 minus half is 1. Half minus 3 by 2 is minus 1. This is allowed transition. But when this spin is undergoing transition or flipping of the states, we call flipping of the state from alpha to beta or beta to alpha, these two spins have the same state. They will not get disturbed. See, this alpha A remains alpha A, alpha M remains alpha M. So only this transition is for X because that is changing the state. Remember, for the transition, the spins has to undergo transition from alpha to beta or beta to alpha state. Otherwise, the transition cannot be seen. Okay, you understand this one. So now let us see few things. Next transition, again X, alpha X to beta X. This is plus half to minus half transition. Plus half to minus half. That is allowed because it turns out to be 1. Another one, this is also allowed. This is also X transition, and this is also X transition. So like that, I showed 4 transitions will be there for A, 4 for M, 4 for X. So without going into the details further, we don't have to see that. We can see what are the possible functions and energy states. We found out there are wave functions are, in simple terms, the energy states correspond to alpha 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 with the spin with the magnetic quantum number of total is 3 by 2, half half half, all those things. Now you can find out the transitions. What are the transitions allowed here? The first state here correspond to sum of all the 3 chemical shifts, A and M and X, half of that. Then you will take JM, JX, JMX by 4. Now you can find out which are the transitions which are allowed. If I take, for example, this to this difference, this will cancel out, only nu X will retain. And then this will cancel, when I take the difference, this will cancel out, and this will retain. So you can find out all the possible transition frequencies and what you can work out how many transition frequencies are there, and with respect to the center of the chemical shift of them, how the peaks are moved, how much it has moved. So you can find out. Take for example this peak. Take the difference between 1 and 2. If I take 1 minus 2, this will get cancelled, this will get cancelled, you will get nu x by 2. Nu x by 2 plus nu x by 2, how much? See, don't get confused here. Look at this one. When I am going to see this one, take the difference. This term gets cancelled out, this term gets cancelled out, and you will get nu x plus nu x by 2 plus nu x by 2 is nu x. And then when I take the difference, this will cancel out, this will cancel out, and this will add up, and this will add up. What does it mean? At the center of the chemical sheet position of nu x, from that position you have one actually peak you have observed whose difference is plus jx plus 2jx and 2jm. I'm sorry, j this by 2 is there. Okay, in this sense, jax by 4, jax by 4, it will become jax by 2. From the position of chemical sheet of x, one peak is there which is moved by j by 2 of as coupling. There is another peak which moved to the right by j by 2 of ms coupling. You can simply find out other one also like this. You can see one more where the couplings will be moving to the left. What is that? You can find out which is which. So in one of the, again another transition, if you see, you can similarly find out there will be two transitions to the move to the left of x. Remember, in the AX spin system, we have one transitions each from the center of chemical shift. But in this case, from the center of the chemical shift of this, for each proton, there will be two transitions to the right, two transitions to the left, depending upon the couplings. From the center, it is, for example, for the X transitions, here you are going to have two peaks, one separated by j by 2 of half of jx, other by half of jmx. Other one you can find out, let me see which is that one to retain nu x. Okay, you take this one. Okay. Okay, you take this one. Minus nu x will be there. Okay, take this one now. What happens? Nu x will be retained, and similarly, these two couplings will be retained, and this gets cancelled out. It means you get two peaks from the center at the chemical sheet position of nu x to the left. Here, two peaks will come to the right. So you get for each spin at the respective chemical sheet position, you get two peaks on the right, two on the left, separated by each of them jax and jmx. Understand? From the center, from the chemical sheet position, half jax to the right and half jmx peak to the right. From the chemical sheet position nu x, half jmax to the left, half jmx to the left. So similarly, you can work out for m and work out for x. You work out for a. All the chemical sheet position, you get 4 peaks. Okay, from the center. In addition to that, are there any additional transitions possible here? If you carefully see, look at this one. Plus half to minus half is 1. All the three spins are changing position. Look at it. Alpha x is going to beta x here. Alpha m is going to beta m. Beta a is going to alpha a. All the three are changing states from alpha to beta. Is allowed. See, any one spin can change the state from alpha to beta or beta to alpha. That's fine. But all the three can change, no problem. But only thing is, as the selection which rule should be obeyed. So this total difference in the magnetic quantum number between these two energy states should be either +1 or -1. That is obeyed. This is called combination transitions. Excuse me. Please remember, when one spin was changing, its particulate one spin was flipping from alpha to beta or beta to alpha like this. This was called single transition, single quantum transition particular to one spin, one transition. But here, all the three is getting changed. This is called combination transition. Is there any other combination transitions you can think of? What about this? This of course we did. What about this? Here also, alpha A, beta A is changing to alpha A, beta M is changing to alpha M, alpha X is changing to beta X. That's also allowed. There's another combination transition. Okay, these three completely is changing to this. That's also allowed. What about this one? Again allowed. Alpha A change to beta A, beta M to alpha M, alpha X to beta X. This is also allowed. And the transitions you can see it is plus half and minus half. You understand about this thing? So now these are all allowed transitions. In this case, not one spin, all the three spins are changing its state from alpha to beta and beta to alpha, vice versa. These are combination transitions. Three combination transitions are also there in these things. But generally, the combination transitions, if you look calculate, you can work out the frequency like this, transition frequency of combination transitions arise at sum and differential values of the chemical shifts. Sorry. It comes at the sum and difference of the chemical shift positions. Okay, look at this. And it contains no J information at all. It doesn't contain J information. You see here, it is coming only at sum and difference of chemical shift positions. You understand? This is the situation here. So, and these are generally very weak intensities and generally not seen only in the strongly coupled spin system. In the weak coupling systems, like A, M, and X, these transitions are not allowed, are not seen. Allowed, but not seen. Whereas in the strongly coupled spin system, which I am going to explain to you later, then these three transitions are allowed. They are seen, but not in AMX. Remember this point, okay? And this is the typical example of a spectrum, AMX spectrum. Okay, typical example of an AMX spectrum where 4 transitions are there for A, 4 for M, and 4 for X. See, 4 for A, 4 for M, 4, which is A and MX is mind convention. The way I want, I can call this A, I can call this M, I can call this X, or whatever the way I want. That is the way I define. The way labeling is my choice. Okay. So now if you look at it, each spin, very interesting thing is you are seeing each of them 4 peaks. See, 4 for this, 4 for this, and 4 for A. From the center of this, you have 2 peaks. Center of this, you have 2 peaks on either side. It could be JX or MX or whatever it is. So each of these peaks at the chemical shift position, each of the 4 peaks, if you analyze, you will get 2 couplings information. Understand? And interesting thing is all are equal intensity. Similar to our AX spin system, where 2 spins coupled, we understood when there is a JAX, 2 coupled spin system, we got 4 peaks. All are equal intensity. Here also, all the peaks are of equal intensity. This is purely perfect AMX weakly coupled spin system. The spectrum appears like this. Now, I will give you some additional information which you must know. Please understand. Carefully listen to me. These are all information which you require very often. If you want to understand NMR in depth, these are all subtle information, but you need to know these things. I am going to now introduce what is called a coupled spin system. What do you mean by a coupled spin system? We have A, M, and X. All the three we understood. This is a coupled spin system. A is coupled to M in the previous example, 3 spins, you took this, I call it A, M, and X. A is coupled to M, A is also coupled to X. M is coupled to A, M is coupled to X. X is coupled to M, X is also coupled to A. So these are all coupled spin system. It's a group of spin system where coupling can be there among all of them. Okay, or let us say I consider five different types of protons are there in a molecule. Five chemically inequivalent protons, all are different. Let me concentrate on proton 1. It can have a coupling with this proton 2. It is possible. That is called J12 coupling. This can have a coupling with this one. That is J13. It can also have a coupling with this one. It is J14. And it can also have a coupling between 2 and 5. Not 1. 2 can have coupling with 5. And 5 can have coupling with 3. 2 can have coupling with 3. 3 can have coupling with 4. 4 can have coupling with 5. What about 1 and 5? Because this is also allowed. There is a coupling here. What about 1 and 5? Right? 1 and 5 is not, there is no coupling. J coupling is 0. But this is a part of the coupled spin system. Remember, there is coupling of 5 to many other protons, and coupling is also there with 4 to other protons. So it is a part of a coupled spin system. Whenever there is a group of spins which are coupled among themselves, we call it a spin system, coupled spin system. There may be several couplings present. No problems. One of them can be 0 also. For example, this coupling is 0, J15. Doesn't matter. But all 5 protons form a system. It is a coupled spin system. You please understand what is a coupled spin system. It is a coupled group of protons where each of them coupled among themselves. There may or may not exist coupling of 1 or 2, doesn't matter, but they all form a system where one is coupled to other. Okay, they are coupled among themselves. And some of the coupling can 0, but the spin must be a part of the, it is a part of the coupled spin system, you see, for all these things. It might be coupled to this, but it's a coupled to other system because others are coupled to this. It is a spin system. Now, a simple example of a spin system is like this. In this example, you take, there are 3 protons here, CH3 and a CH2. Just an example I am giving you. This CH3 can couple to CH2. Is allowed because there is no problem. What 3 bond coupling is, it is possible. This can couple to this and this can couple to this. No problem. But you see, 1, 2, 3, 4 bonds away. 1, 2, 3, 4, 5 bonds away. So this CH cannot couple to this CH3. This CH2 and this CH3 coupling is 0. There is a break in the system now. Break in the coupling. So that means what happens is this coupling exists, this coupling exists, and this coupling do not exist. This is one coupled spin system and this is another coupled spin system. You understand? Here none of these protons are coupled to any of them. So it doesn't form a part of the coupled spin system. For the part of the coupled spin system, at least all the couplings may not be there, at least some of them should be there. All coupling, if they are 0, that means it is not in the coupled spin system. So there are, in this example of the molecule, there are 2 spin systems. This forms one coupled spin system, this forms another coupled spin system. I hope you are all able to understand. I hope you are all with me. If let us say there was one proton here and the coupling was there and it was there, this coupling may be 0, but still it would have been a part of, the entire group would have been part of spin system. But because there is a breakage in the chain here and none of these protons are coupled to this, they are all different spin systems. They do not form one spin system together. Okay. Now, the spin system we can classify very easy. There is a rule for it. We can classify. What do you mean by classifying spin system? Like, I can classify them as weakly coupled and strongly coupled. Remember, when I was analyzing the 2 spin system AX, I said they are weakly coupled. What did I say? Because the chemical Schutz separation of these 2 should be larger, sufficiently larger than coupling between them. Here is the X spin, it is the X spin, chemical shift. This separation may be 500 Hertz. Coupling is about 10 Hertz. Where is 10 Hertz and where is 500 Hertz chemical shift separation? It is quite large, right? Chemical shift separation. That is why we call such system where chemical shift separation is sufficiently large several orders of magnitude larger than the coupling, we call them as weakly coupled spin system. On the other hand, if the chemical shift separation is comparable or equal to chemical shift separation to J coupling, they are strongly coupled. I give an example here. Look at this one. If I take the J over delta delta, what is J? J is actually, if you see that, J will be about 10 hertz. Take us 10 hertz here. And divided by chemical shift separation, let us say 500. What is the difference now? If much smaller than 1, right? If you look at it, it's much smaller. Now come here. In this case, J and delta are comparable. J is 10 hertz and delta separation is also, let's say, 15 hertz. What is this? This is of of the order of 1. Here this is much smaller. 10 by 500, where you are 10 by, let us say, 1000 I will take for easy to compare. Then it is 0.001. This is much smaller than 1, and this is a weakly coupled spin system, whereas this one is a strongly coupled spin system. You understand this one. Please do not get confused. In this example, what I'm trying to say, okay, in this case, J by delta is much smaller. Delta chemical shift separation is much smaller. That means this has to be a very large value than weakly coupled spin system. If they are comparable or of the order of 1, then it's strongly coupled spin system. This is a very important point you should remember. And the spectrum is entirely different if it is strongly coupled and weakly coupled. And especially when they are very strongly coupled, the spectrum will appear entirely different. Remember that point. Look at the example of this spectrum of 2 coupled spins. I said we took the example of 2 AX spin coupled, we got 4 transitions. We calculated, right? By looking at the transitions. 2 for A and 2 for X. That's what we observed, right? Here we got 2 for A and 2 for X. This is weakly coupled spin system. Look at the chemical shift separation, about almost 7.5 to 6.7 to about 1 ppm. In 500 megahertz, 1 ppm is 500 hertz. What is this separation? It's only of the order of 10 or 15 hertz. So it is weakly coupled, and they must be of equal intensity. See, in principle, all these 4 lines should be of equal intensity. Look at this one. All these 4 should be of equal intensity. But do you see this? No, not of equal intensity. It means it is still at 100% weakly coupled. There is some sort of a strong coupling character put in this system. There is some sort of a strong coupling character present in this. So this is weakly coupled. More or less you assume the equal intensity and weakly coupled. What is the strongly coupled? The strongly coupled looks like this. Look at this one. This spectrum is a 2 spin coupled. This is also 2 spin coupled. But this is 4 lines of equal intensity, well separated. Whereas in this case, look at it. It looks like 2 very strong peaks at the center, 2 very weak peaks outside. This is the pattern of a 2 coupled spin system, especially with the strongly coupled. I am going to discuss more about strong and weak coupling when I try to analyze this theoretically by using Pople nomenclature, how we can analyze the spectrum. I'll come to that later. We will use the Pople notation. When I say AX, AB, AMX, I use the term AX and AMX. When do you want to use it? We will discuss all those things later. Okay. So now, with this idea, you got some idea about the multiple strong coupling, weak coupling, spin system, and also I explained to you what are the transitions for 3 spin system like A, M and X weakly coupled. 4 A transitions we got for A, 4 for M, 4 for X, and we also saw in such system there are 3 combination transitions where all the 3 spins can simultaneously change states from alpha to beta and vice versa. Normally only one spin will change from alpha to beta or beta to alpha. Others will remain same. Their state will not change. But in some examples, all can change, but still maintaining the selection rule. They are called combination transistors. All those things we understood, something about information about scalar coupling and everything. Now, most important part, we will understand how this scalar coupling influences the spectrum. So far, you take the example of 2 spins and 3 spins. You got 4 peaks. You got 12 peaks in AMX. Very easy. I can show you how we analyze later. We can easily get the chemical shift and coupling constant. What happens? There are more protons are coupled. Will you get only 4 peaks of equal intensity? Will you get only 12 peaks of equal intensity? We do not know. Again, depends upon the spin system. Depends upon how strongly they are coupled, how weakly they are coupled, how the multiplicity will be there. Whether it is a 4 peak, 10 peak, 12 peaks. What is the pattern? We do not know. We have to understand that. As a consequence, I'll introduce to you something about what is called multiplicity of the spin system. Please remember, I am going to introduce to you about multiplicity of the spin system here. What is the multiplicity of the spin system? First, start with the isolated proton, isolated spin, or any molecule containing only one proton. In the consider an example of CHCl3. I am looking at proton spectrum. What are the other spins which can interact here? What are the other NMR active spins? Carbon 30, chlorine 35. It is a quadrupolar spin. We will ignore it. Assume that it doesn't couple. Carbon 13 is there. That can couple to this. But carbon 13 is a very low natural abundance. Only 1%. This what you should remember. As a consequence, temporarily, for the time being, we will assume carbon 13 coupling to proton is not there. Even if it is there, we don't, very small intensity is there, we will not bother about that coupling. We will assume that molecule has 99% carbon 12 attached to CHCl3, carbon 12 HCl3. We will consider 99% molecule, not 1% will not worry. Then if that is the case, it is like telling a isolated single spin system, because it doesn't couple to this, this doesn't couple to this, and this is a carbon 12 isotopomer. What are the possible energy states for this? There are two orientations of the magnetic moments, plus half and minus half. This is allowed transition. We have been discussing in the selection rule also we discussed. So this spin can go from alpha to beta and beta to alpha. This transition allowed, because minus half to plus half to minus half is always plus or minus 1. So this is analogous to a single spin uncoupled spin system, in which case you get only single transition. Isolated spin half always gives a single peak. This is a classical example I will give you. Take an isolated proton without any coupling to any other spins. Take a molecule like this. A hypothetical molecule I have generated. I have put proton here. Carbon with some X, Y, Z I have attached here. None of them coupled to this. Then how many peaks you get? Only one peak. It is a singlet. That is an example. Now we already discussed transition into uncoupled spin system. When AX is not equal to 0, we already discussed. Now take an example like this. Proton A and X. Assume this coupling is 0. When I make JAX is 0, what will happen? You will get one peak for X and one peak for A. Remember, a singlet is detected for A and a singlet is detected for X. This is what we observed. When we have two spins which were non-interacting, we found from the energy level diagram there are 4 transitions, 2 for A, 2 for X, identical frequencies, they were overlapping. So as a consequence, we got one peak for A, one peak for X. Please remember, we worked it out in one of the classes, 2 classes before, for 2 non-interacting spins, we calculated, we found out the transition, right? We got one transition each for A, one transition for B, for X. In reality, there are two peaks overlap. Let us consider the intensity of this is 1. They are all equal intensity. They overlap, equal intensity will be there. And if I assume similarly in the previous case, delta X is larger than delta A, I get only 2 peaks. This also we understood. Of course, we understood this also. Two weakly coupled spin system. Proton A gives 2 peaks and proton X gives 2 peaks, and we also got 4 peaks. This also we understood because we discussed today. Now, one interesting, important information I want to give you. Please remember, interactions among spins in NMR are always mutual. Remember, interaction among spins in NMR are always mutual. If proton A is coupled to X, proton X is also coupled to A. Remember that. If proton A is split into doublet because of its coupling with X, similarly, doublet of identical splitting is also seen for X because X is also coupled to A. This is one of the important points you remember. Interaction among spins in NMR are always mutual. Okay. So now coupling between two non-equivalent spins if I take, we already calculated by the energy level diagram we have found out it will give rise to two spins. Proton X sees A in two energy states, X will see A in two energy states. As a consequence, this will split into a doublet and this will also split into a doublet. And this is JAX, this is equal to JAX, and this center gives chemical shift of X, this gives you chemical shift of A. Okay, so one second. What I will do is more about the multiplicity pattern for other spin systems. I am going to start later from tomorrow. But today, for this point, I will stop at this place. We have understood quite a bit about scalar couplings today. Now we have come to the level of interpreting the multiplicity pattern. I just took the example of some hypothetical molecules which you worked out from the energy level diagram, and now I am telling you how does spectrum come. With this, we go further. One important point you must remember what I said today. Interactions in NMR are always mutual. If A is coupled to X, X is also coupled to A. If X is split into doublet because of coupling with A, identically same doublet will be seen at A because it is coupled to X because of mutual interaction. So these are all the important points. We use these to go ahead and analyze the spectrum. So I'll stop here. We'll see tomorrow.